So welcome. Last lecture we have seen friction in pipe and how do we estimate the friction factor and how do we use that now. That's what we are going to see in this lecture. So just to refresh your memory, uh, uh, this is where we are in the course. We are talking about Bernoulli equation and their engineering applications, pressure drop in pipes and fittings, internal flows. Just to quickly revise what you have done, what is meant by fanning and Darcy friction factor. Write an expression for head loss due to friction in terms of fanning friction factor. Write an expression for head loss in terms of Darcy friction factor. What is meant by Reynolds number? How do we calculate that? We will see that. We'll do these calculations now. What is meant by rough and smooth pipe and how do these friction factors depend on rough and smooth pipe? Moody chart, do you recall? And all these equations that we saw in the last class. And now let's start using all this and estimate the power required for the pump. So here is a problem. Before that, the standard pipe sizes also we saw, recall from the previous lecture. Okay, so here is a problem for you. We want to transport water from one location tank at the ground floor, let's say, to another tank at the top of the building. Let's say this could be tanks, this could be reactors, this could be distillation column, different equipment in the plant. We are just using it for water, just for the simplicity. So the question that is to be answered is how much pump power is required to make water flow from 1 to 2 through the pipeline. And here are the things about the pipeline. So we want to have a water flow rate of 25 meter cube per hour. A meter cube, okay, it should be meter cube, not m3, it is meter cube. Okay, 25 meter cube per hour. Now I need to give you some properties of water. So water has a density of 1000 kg per meter cube. It is a meter cube. So density of water is 1000 kgs per meter cube. Viscosity is 0.001 Pascal second. Just a little bit about this viscosity. So the SI unit of viscosity, mu is the viscosity. So viscosity for water, it is 0.001 Pascal second is the SI unit. So it is Newton per meter square, that is Pascal, multiplied by second. Okay, so that's the unit of viscosity, SI unit of viscosity. We'll see a little bit more details about what this viscosity is, how to calculate it, why is there a viscosity, why different fluids have different viscosity, and so on. Another unit of viscosity you might have heard is called as poise. Poise, P-O-I-S-E. And a shorter unit you might have heard, centipoise or CP. You might have used some of these things in your 11th and 12th. And so rather than writing 0.001 Pascal second, sometimes we write it as 1 millipascal second. Millipascal, milli is 10 raised to minus 3. Remember our suffixes and prefixes that we have been using. Millipascal second, 10 raised to minus 3 Pascal second. So 1 millipascal second is 1 centipoise. Okay. These are just some of the conversions and from the commonly used units. We will see all these in a lot more detail as we go along. Right now, I just have to give you a value of viscosity. So the water viscosity is, let's say, 1 millipascal second, 0.001 Pascal second. So let's say this pipe diameter is 2 inch, schedule 40. Remember what schedule 40 means? 2 inch, schedule 40 means the inside diameter is 52.5 millimeters, almost 2 inch. 2 inch would be 25.4 multiplied by 2, slightly more than that. Okay. Let's say both these tanks are open to atmosphere, so P1 and P2 are the same, it's open to atmosphere. H1, let's say height of water in this tank, let's say this tank is very close to ground, so this height difference in the tank is very small, so let's say H1 is 0 meters, okay, and H2 let's say is 10 meters. The second tank, overhead tank, is at a 10-meter location from the ground. I would like you to find out how much is the power required. That's what we need to find out. Solve this for yourself. Pause the video. Use all the things that we have seen in the previous lectures. Pause the video. Okay, here is the solution. What we are going to do, we are going to write Bernoulli equation, right? Velocity in location 1, velocity in location 2, they are almost the same, right? So our Bernoulli equation, if you remember, v1 alpha 1 v1 square by 2, alpha 2 v2 square by 2, they will just cancel out. Velocities are small and they are anyway approximately same. P1 minus P2 are the P1 and P2 both are atmospheric, so P1 by rho g, P2 by rho g, that will cancel out. So write your Bernoulli equation in front of you, cancel out the terms as I am speaking. P1 by rho g and P2 by rho g, they will cancel out from each other. H1 is 0, right? So HP, the pump power, anyway this equation was there in the previous video, you can see for yourself. HP, the pump head that is to be added by the pump, is H2 minus H1 plus P2 minus P1 by rho g. Pressure head to be added. Now this term is 0 because P2 and P1 is the same. Okay. So now pipe is 2-inch schedule 40. So pipe inner diameter ID is 2.067 inches, that is 52.5 millimeters. So now we know the flow rate 25 meter cube per hour, that's what we want. Okay. We can calculate the velocity. How do we calculate the velocity? Velocity is flow rate divided by cross sectional area, pi by 4 d square. Take care of units. It is 25 meter cube per hour. 25 divided by 3600. So many meter cube per second divided by pi by 4 will be as such, pi by 4. You can calculate that. Diameter, it is 52.5 millimeters. Take care of units. So in terms of meters, if I want to write, it will be 0.0525 meters, and square of this pi by 4 d square. That will give you the velocity in the pipe. So velocity you will find is 3.2 meters per second. Reynolds number, if I want to find out, what is Reynolds number? It is diameter into velocity into rho by mu. Diameter, it is 0.0525 multiplied by velocity. Velocity is 3.2. All these things would have become so much easier on the board. I have to struggle to write on the slide. 1000 with a mouse would have been easier with a touch screen as well. dv rho, doesn't matter, dv rho by mu 0.001, all in the name of education. So Reynolds number you will find it is 1.7 into 10 raised to 5. Now if I use any of these friction factor equations, for that I need to know the roughness. Let's say roughness is 0.001. I told you that. Did I tell you that? Okay, let's assume roughness is 0.001. Now any one of these equations that we use, let's say if we use Swami and Jain equation, you will find that the Darcy friction factor is 0.021 and the fanning friction factor is 0.0053. Now HF, head loss due to friction, is 2. F, V square, remember the formula for HF, let me write that as well. HF is 2F fanning friction factor, V square velocity in the pipe, V square, L, rho will cancel out, D and G. So that is 2F friction factor 0.0053, velocity square 3.2 square, length is, let's say, 205. Where is the length? Yeah, length is 205. Why we are saying 205? This length between one and the pump is 5 meters, and between pump and the top is, let's say, 200 meters. Why we want the pump to be near the inlet tank, we will see later on. But let's say this length is 5 meters and this length is 200 meters. So total put together, water has to flow through 205 meters of the pipe. Another question you may have is, this height difference is only 10 meters, then why do we require 205 meters of pipe? Okay. Because pipes are not directly connecting the 2 points. Pipe will go along the wall, maybe there is a balcony somewhere, maybe there is a parapet somewhere, so the pipe has to go around, maybe it has to go around one corner of the building and up through, so that it is not visible very nicely, it does not affect the aesthetics. So all those considerations come into pipe. So the height difference, vertical height difference, may be just 10 meter, but the path that the pipe takes, maybe it is routed through different locations for various purposes. So these are, it is not just that pipe is joined by a straight line between the 2 points. So the pipe length is much more than what the height difference would be. Okay, so this is the length of the pipe. F V square, we have done L. D is 0.0525, I have just approximated to 0.053, and G 9.81. So you'll find that HF is 43.2 meters. Okay, so the head that pump has to add, energy, power that the pump has to add, is corresponding to H2 minus H1, that is 10, plus this HF, so 10 plus 43.2, 53.2. Now what is the power that the pump has to deliver? Let's write that. Power that the pump has to deliver is HP is the head that pump has to add, rho G and Q. Q is volumetric flow rate. Take care of units. Q is in meter cube per hour. You have to convert that to meter cube per second, like this. This is meter cube per second. Okay. HP is 53.2, rho 1000, G 9.81, Q 25 divided by 3600. So you will get power as 3.625 kW or 3625 watts. Divide that by 1000, you will get it as 3.625 kilowatts. So if the pump is, let's say, 70% efficient, how much power it will draw from the electrical supply? It will be 3.625 divided by 70%, divided by 0.7, it will consume 5.2 kW. So this pump power will have to be 5 kW, because 70% of that 3.625 is what is going in the fluid, in making the fluid go from location 1 to location 2. So if you want electricity cost, we did all these kinds of calculations. If it is running for 8,000 hours in a year, then this is 5.2 into 8,000, that is so many units of electricity. If one unit costs 10 rupees, then its expenditure is 4.16 lakhs per year. Okay. Compare this with the salary that you are going to get, or salary that our graduates get, maybe 5 lakhs, 6 lakhs per year after you graduate, right? So cost of electricity, cost of friction, you see frictional head loss was 43, whereas actual height difference is only 10. Okay. So friction is very important. We need to consider friction. Without that, we would not get the correct answer. Okay. So let's go forward. Okay. Make sure that you have done this correctly. Make sure you understood all these concepts, all the calculations. Then let's go forward. let's do another problem. So let's calculate pressure at the pump suction and pump discharge. So let's say point number 3 is at pump suction and point number 4 is at pump discharge. Okay. Same situation as earlier, water flow rate is 25 meter cube per hour, rho is 1000 kgs per meter cube, mu is 0.001 Pascal second. Everything is the same. Pipe diameter is the same, lengths are the same, everything is the same. We just have to calculate P3 and P4, pressure at the pump suction and pressure at the pump discharge. Everything is the same. Okay. Just to, before you solve, let me just give you a hint. Write Bernoulli equation between 1 and 3. You will get, simplify that, you will get P3. Write Bernoulli equation between 4 and 2. You will get P4. Okay. Pause the video, do it for yourself. Okay, here is the answer. So we write Bernoulli equation between 1 and 3 and simplify. Okay. So alpha 1 V1 square by 2G plus H1 plus P1 by rho G plus HP, alpha 3 V3 square by 2, well, this should be 2. Let's wait, let's make this correction. Yeah, so V3 square by 2G, H3 P3 by rho G, and now HF between 1 and 3, because we are writing Bernoulli balance between 1 and 3. Now velocity in the tank is very small as compared to velocity in the pipe. V3 is nothing but velocity in the pipe. That's 3.2 meters per second. Velocity in the tank is very small. So V1 is very small as compared to V3. So V1 square by 2G I can neglect in comparison to V3 square by 2G. Pressure is 1 atmosphere absolute, P1. H1 and H3, they are almost the same. So we are going to cancel them out. Almost the same. They may or may not be same. In this particular case, they are approximately the same. There is no pump between 1 and 3. So this is 0. So then you will find that P3 by rho G would be equal to P1, P atmospheric pressure divided by rho G minus alpha 3 V3 square by 2G. Well, this also should be 2G. Let's make that correction. Yeah, it's corrected now. So this is 0 as compared to alpha 3 V2 square by 2G. H1 and H2 we have cancelled out. H1 and H3 we have cancelled out. HP, there is no pump. So now V3, P3 by rho G would be P atmospheric divided by rho G minus alpha 3 V3 square by 2G minus HF between 1 and 3. So now you can easily calculate velocity, you know, HF we know for the whole pipe. Now HF between 1 and 3 is just proportional to length, that's all. So now P3 we can calculate. Similarly, if you write Bernoulli equation between 4 and 2, alpha 3, just a little bit about alpha 3. Alpha 3 flow is turbulent. Reynolds number is something into 10 raised to 5, very large. See, Reynolds number is very large, 1.7 into 10 raised to 5. Flow is turbulent. That means alpha is 1.06. I can even neglect that 1.06. I will make only an error of 6%. And anyway, the kinetic head is not very large as compared to the pressure, as compared to the friction. So now similarly, if you write between 4 and 2 and simplify, P4 by rho G, you will get to be H2 plus atmospheric pressure by rho G plus friction head loss between 4 and 2 minus the kinetic head at 4. Okay. We want this number between, we want this. Right. H4 is practically 0. H3 and H4, they are the same, right? P2 is atmospheric pressure. HP, there is no pump between 4 and 2. So P4 by rho g would be this, alpha 2 V2 square by 2g. Velocity in the tank, very small. Okay, alpha 4, yeah, sorry, this alpha 4 V2 square by 2g, this is there. This is important because velocity, this is velocity at 4, it is in the pipe. So this is 3.2 meters per, it is not negligible, it is important. Make that correction. Sorry about that. So bring this on the other side. P4 by rho g would be H2 plus P2 by rho g, which is the atmospheric pressure by rho g, plus frictional head loss minus the kinetic head that is available at location 4. So do these calculations for yourself. You will find that P3 is something like 0.7, 0.8, 0.9 atmosphere, almost equal to 1 atmosphere, but slightly less than 1 atmosphere. P4 is almost like 40-50 meters. P4 by rho g is almost like 40-50 meters, because that much is the head that it has to overcome. Right? So calculate for yourself. Let's take another problem. So here is another problem. Sometimes the flow of fluids is by gravity. So here is one problem. There is no pump used now. So let's say we have transported water in the overhead tank. Now people are using this water in their building, in their house. So water comes from the overhead tank. So this is the overhead tank. Water comes down and it comes to this person using this water. Let's call this as location 2. Okay. So let's say this pipe is 2-inch, schedule 40. Let's say length is 100 meters. Just take some number. P1 and P2 are 1 atmosphere. Tank is open to atmosphere. When this person opens a tap, it is open to atmosphere. Water comes out at atmospheric pressure. So P1 and P2 are the same. They are 1 atmosphere. H1 now is, let's say, 20 meters. We have taken in the earlier case 10 meters, 10 meter tank. Let's just take another value, another problem. It's like a tall building if you want. H1, height of the liquid in the overhead tank is, let's say, 20 meters. H2 is 0 meters. It's a, let's say, ground floor. And V1, velocity in the tank, is very small as compared to velocity here. So meaning of that is the tank is very large, heights don't change, as if the height is constant. What would be the flow rate at location 2? That's what I would like you to answer. So use Bernoulli equation, use friction factor, all those things, calculate for yourself. Pause the video now. Okay, so here is the solution. Here is how to do this problem. So let's think about applying Bernoulli equation, right? So between 1 and 2, so alpha 1 V1 square by 2g, P1 by rho g, H1, HP, alpha 2 V2 square by 2g, P2 by rho g, H2, HF between 1 and 2. Now what can we say about P1 and P2? Both are open to atmosphere, so they'll just cancel out. H2 is 0. V1, velocity at location 1, is very small as compared to velocity at 2. So V1 square is even smaller as compared to V2. There is no pump between 1 and 2. Flow is now only occurring because of gravity. So this is not there. Okay. So what equation we will get? H1 will be equal to V2 square by 2g. Now alpha also I have substituted as 1.06. Therefore I have neglected that. Alpha is almost 1. Even if I make it 1, I am only making an error of 6% in this part. And then the frictional head is significantly larger as compared to this. So we don't make that much error even if I neglect alpha. Alpha is 1 for turbulent flow. And HF between 1 and 2. So H1 would be V2 square by 2g. HF we can write 2F friction, 2F V square, velocity in the pipe. So velocity in the pipe and velocity at 2, they are the same. At steady state, water is not accelerating because it is opposed by frictional force at the wall. So just like we had pressure difference balancing out the friction at the wall, therefore water flowed at steady state, did not accelerate. Same way here, flow of water in the pipe, there is friction at the wall. That frictional force is opposing the gravitational force. It is exactly counterbalancing. That's the steady state flow rate that we will get. So velocity in the pipe is same as velocity in the at location 2. So 2f v square L between 1 and 2 divided by d and g. So immediate problem is, I know h1, this is known, g is known, d is known, g is known, L12 is known. I don't know velocity. That's what I need to find out. This is what I need to find out. But the problem is this friction factor itself depends on the Reynolds numbers, which itself depends on velocity in the pipe. So we are stuck. We have two unknowns, friction factor and velocity, and we have only one equation that is coming from Bernoulli equation. So let's see how to solve. I don't know friction factor because that depends on velocity in the pipe. But can I make an assumption that flow is laminar here? Let's do that. So if I say flow is laminar, that means Reynolds number is less than 2100. I can say fanning friction factor is 16 by Re. Recall from the previous video, previous lecture. So now I can substitute this. H1 would be V1 square by 2G. 2, 16 by Re. Velocity square L, D and G. Nothing but 32 mu L. This is like the Hagen-Poiseuille equation. 32 mu L by D square. Hagen-Poiseuille equation. Okay, we'll see that as we go along. So now I can substitute 20 V2 square, that's unknown, by 2G, 0.051 V2 square. Simplify this. 32 mu 0.001. Velocity is unknown. L12 is 100. Yeah, 100. D square 0.0525 square, rho 1000, G 9.81. So you'll get it as 0.12 into V2. Now this is a quadratic. We can solve for V2. V2 would be 18.66 meters per second. So if I assume laminar flow, I get a velocity of 18.66 meters per second. But is this right? Well, let's check. Let's calculate Reynolds number again. It will be D V2 rho by mu. You will find that Reynolds number is 9.79 into 10 raised to 5. This Reynolds number is not less than 2100. So our assumption is wrong. This assumption is wrong. Friction factor is not 16 by Re. So let's say flow is turbulent now. Let's assume flow is turbulent. But now there is a problem that friction factor and Reynolds number, there is a relationship equation that I need to add. I need to put in here. If I say pipe is smooth right now, okay, we have not said pipe is rough right now. Let's say pipe is smooth right now. Then I can use this Blasius equation, 0.079 Re raised to minus 0.25. It's called as a Blasius equation. I can put that here. So H1 would be V2 square by 2G. 2F, that's the expression, velocity square L divided by dg. Put the values. 20.051 V2 square, 2.079 L12 dg, d rho by mu raised to minus 0.25 and velocity raised to minus 0.25 and velocity square I have combined as velocity raised to 1.75. So if you simplify, you will get 20.051 velocity square, 2.027 velocity raised to 1.75. Now we can solve this and get a value of V2. Either we can solve on a calculator, or let me just show you how to solve in Excel. Let's put this equation. Let's put this equation in the Excel. Right? What I need to do for that, let's see, open Excel. Yeah. So V2. right? Let's just take some guess value of V2. Let's say 2 meters, okay, or let's say previous value, some 18 meters, something like that. Now we need to put this equation. Okay, what is our equation? It is 0.020, 0.051 V2 square, 2.027 V2 raised to 1.75. That's our equation. Let's put that in Excel, right? So I'm going to put a formula. We have 0.051 multiplied by V2 square, okay, plus, right, let me just put that, okay, okay, let's put the equation 0.051 V2 square, 2.027 and V2 raised to 1.75, 2.027. This is 0.051 V2 square plus 2.027 multiplied by V2 square. And what we want this value to be 20 equal to H1, right? So what we can do is you go to data, what if analysis, goal seek. We are going to say that this formula, value of that formula has to be 20, and we want to change this value of V2 to do that. Okay. Yeah, so it has found that the value of the formula is 20 and the corresponding velocity required for that to get to this 20 is 3.1 meters per second, right? So the we can use that. Yeah, so if you do this, you will find that velocity might have made a slight change in the formula, might have made a small error in the formula, but this velocity is now 3.63 meters per second. Okay. Now let's check whether Reynolds number is right. Reynolds number is dV rho by mu is 1.88 into 10 raised to 5. Right? So our assumption that Reynolds number is greater than 2100, flow is turbulent, this is right. So we are okay, we are correct in using this formula, but we are wrong in using this assumption of laminar flow. So because velocity is not known, we need to do this by sort of assuming whether the flow is laminar or flow is turbulent, and therefore we need to do this. Let's take one more problem. So imagine now the same situation, overhead tank, somebody is using this water. Now instead of one pipe, now there are two pipes. Somebody is using the water in, let's say, third floor as well. Okay. Same problem as earlier. H1 is 20 meters, H2 is 0 meters, H3 is 10 meters. Now let's say 2-inch pipe, schedule 40. Now length between, now let's take one more point here, 4. So length between 1 and 4, 50 meters, length between 4 and 2, 50 meters, length between 4 and 3, 50 meters. I would like you to find out what is the flow rate at 2 and 3. Okay. Do this for yourself. It's a little tricky problem, but do it for yourself. Okay. I'm not going to give you a solution. You do for yourself. Okay. We will discuss the solution if you require. Okay, here is some more thoughts from this equation. Our head loss due to friction is delta P by rho g, or if you think in terms of friction factor, 2F V square L by dg. I can write this equation in terms of turbulent flow. So 2F velocity is Q divided by pi by 4 d square whole square L by dg, and I can rearrange this. I will get 32 F Q square L pi square d raised to 5 d square whole square and another d, so d raised to 5 by g. This equation tells us how the head loss due to friction is dependent on diameter of the pipe and flow rate. So if I double the flow rate, frictional head loss will become 4 times. Even if I say that friction factor is a weak function of Reynolds number, recall from previous lecture, Moody's chart, friction factor versus Reynolds number was almost a horizontal line at very large values of Reynolds number. So HF would be proportional to Q square and D raised to 5. Now imagine that this pipe becomes rough, it becomes corrodes and things like that. So it becomes rough. So diameter reduces. So if diameter reduces, frictional head loss increases. Even if I have a 5% reduction in diameter, leads to 30% increase in the friction and the pressure required or the head required for overcoming friction. Even a small amount of corrosion, that's why when you are in the plants and pipelines foul with respect to time, foul in the sense accumulation happens, corrosion happens, rust accumulates, it leads to a reduction in diameter. The same pipe which was working very beautifully transporting the fluid, now frictional head loss has become 30% more. Okay, that's why it is important to take the pipe of appropriate size. We will see that in another problem later on. Another implication in terms of blood flow in arteries. So if you eat too much junk food, what happens to the artery? There is a coating, cholesterol lining, the diameter reduces. So even if diameter reduces by 5%, small reduction, it requires 30% more head in terms of in order to overcome friction. That much amount of extra pressure has to be generated by the heart to make the blood flow go at the same rate. And if heart cannot generate that much amount of pressure, the flow will reduce, and therefore you see numbness in the extremities, numbness in the head, maybe giddiness in the head, because brain does not receive that much amount of flow. It is because of friction. Okay. Another situation is, now let's say there is a person, let's say this person is idle, or let's say this person is resting. He requires very small amount of blood flow, maybe few liters per minute. But if this person is exercising, let's say this person is jogging, running and so on, the blood flow required is much more. Okay, the head required to overcome friction will become square of the blood flow required. So if blood flow is, let's say, instead of 5 liters per minute, it requires now, let's say, 6 liters per minute, let's say 20% more. 20% more blood flow will require 40% more head loss in overcoming friction. It will require 40% more pressure to be generated by the heart. Obviously, heart does not generate 40% more power. It is dependent on the muscles. So what happens is these arteries dilate. When arteries dilate, diameter goes up. If diameter goes up even slightly, diameter raised to 5 is enough to compensate for the extra blood flow during exercise, and heart can pump at a normal pressure. Okay, so these kinds of flow situations are very important in biological systems. Okay. That's why it is also important to choose a pipe size correctly. We'll see a problem little later on. Okay. So this is where we will stop this lecture. What we have seen is how to relate energy required, power required by the pump to flow, say 25 meter cube per hour or whatever is the flow that we want, and the geometry, what pipe size I have, what pipe length I have, okay, what pipe diameter I have. So the first lecture, what I talked to you about, flow, geometry and power, that's how they are related, and that's how we have been able to calculate them from the Bernoulli equation. Okay, so we'll stop this lecture here.